Hey everyone, welcome to my channel. This is part 7 of the self-driving car simulation using convolutional neural networks. In this video, we are going to create and compile the model proposed by Nvidia for their end-to-end self-driving. So let's get started. So next we are going to create, so I think we are done with step number 7 as well. Step 7. So next we are going to move on to step number 8. And step number 8 is basically creating the model. So we are going to use Nvidia's model that they have used, and we are going to go step by step and create that exactly as it is. So what we can do is we can import. First of all, we will go to utilities, and over here we are going to write the model. So we have to import Tensorflow, from which we are going to create our model. Now Tensorflow, inside Tensorflow we have Keras. Now we don't have to import it separately, so we can just say from Tensorflow dot Keras, let's say dot models, we are going to import sequential because we have a sequential model. And then from Tensorflow dot Keras, we are going to import layers, and we are going to use convolutional layers. So convolutional, is it capital? No, convolutional 2D, yeah. And then we will use flatten, and then we will use the dense layer. So all these layers are in the Nvidia's model, that's why we are importing all of them, and we will be using them. So then we will write from Tensorflow, we want to import dot optimizers, and we are going to import our Adam optimizer. This is one of the most common ones, and we will be using the Adam optimizer. So here we will write create model, and we don't need any arguments. We will write here that our model is basically sequential, and then we are going to start adding our layers. So as you can see in Nvidia's model, we have the input planes at first, which are 200 by 66, and they are 3 channels. And then we have applied the normalization, and after the normalization we have our first convolutional layer, and you can see the kernel is 5 by 5 and the filter size is 24. So we can write this down. We can say that model dot add, and we want to add our convolutional layer, so we will write convolutional 2D, and inside the first parameter is basically our filter, which is 24, and then we have the kernel size, which is again mentioned 5 by 5, and then we have the stride. So the stride is basically the jump that the kernel size will take in the X and in the Y direction. So we will say that 2 by 2. Now this is 2 by 2 because you can look at the feature map of the convolutional layer and you can find out this value. I will explain this a little bit later as well. So for now we will just move on. So the input shape you have to define as well. So our input shape is 66 by 200 by 3. And the last thing is the activation function. So in most cases we are using ReLU, where negative values become 0 and we have the positive values, and this is basically a non-linear function. But the thing is, ReLU does not work very well in this particular example. So we will be using a similar activation function, which is basically LU, which also has the negative element. So we are going to use LU. Now as you can see, the next layer is pretty much the same. So we are going to copy this, and we are going to copy this, and over here we are going to define the filter size, which is 36, and then we again have a 5 by 5 kernel, and then we have the stride of 2 by 2, and the activation is again LO. Now we do not need to define the input size because it will calculate by itself. Then the next one is again a convolution layer, and then we have 48, and then we have 5 by 5 and 2 by 2, and then again LO. So then we can paste this again. Actually we have two more convolution layers, so what happened there? So we have two more, and this time around we have the size of 64, and then we have the size of 64 again, and we have the size of the kernel of 3 by 3. And this time around we will have the stride of 1 by 1. Again, I will just show you momentarily why are we using 2 by 2 here and why are we using 1 by 1 here. Next we have the flatten layer, so we are going to flatten everything out. So we will write here model dot add, and we will write here flatten, and then we have our dense layers. So we will write here model dot add dense. So the first one we have has 100 neurons, and the activation function, again we will put this as L. So we have four more dense layers, so we will duplicate these, and as you can see here that we have 50 neurons, and then we have 10 neurons, and at the end we should have only one value, and that will be our final output. So we will remove the activation. And the last thing we have to do is we have to compile our model. So we will write model dot compile, and then we are going to write that we want to use the Adam optimizer with the learning rate of 0.0001, and then we are going to write the loss. Now we will use one of the most common loss functions, which is mean squared error, MSE. Now we are using MSE because this is a regression problem. We are having a continuous output, so we are using MSE. Now then we have to return this model, return model. So if we go back here, we are going to write down model is equals to create model, and then we are going to write model dot summary. So this will print out the summary for us. So let's run this and see what happens. Okay, there is a mistake somewhere. If we go back, and the mistake is here. Oh, okay, so the mistake is actually here. So we have to write brackets in front of it, and now if we go back and we run, and there we go. So now we have the summary of our model. So now you can see that the feature maps actually match with our Nvidia's model, which is as you can see, the first one is 24 filters and the size is 31 by 98. Then in the second one it's 14 by 47 with 36 filters, and then you can see each one of them actually with the same values. And at the end we have the dense layer where we have 100, 50, 10, and at the end we have one value. Now regarding the stride, if we make the stride 1, we will not get the feature map that we are getting here right now. Now the reason why we have stride of 2, I think in these three we have the stride of 2, and then we have the stride of 1 for these two. And the reason for that is, if you look at the image size for these three images, the image size is still large, so we can accept the 2x2 stride, so we can jump around quite a bit. But for these two images, you can see that the 2x2 stride would actually not work. It will give you an error. So that's why the images are very small, so they are using a stride of 1x1. And at the end we can see that we have total parameters of 250,000, which is very close to what Nvidia has shown in their actual model. And regarding all of this, these are just warnings, and you can see most of them, it just shows successfully opened, and this will be shown if you are using a GPU. So you can see here I have the I have two GPUs here, both of 5.2 capability, and if you are not using the GPU, all of these warnings will not show up. So if you don't want to see this, if you are like me and you want to remove these, what you can do is you can go to your main script, and over here you can add because it takes a while, I like to print something so that I know that it's running. So I can write here setting up, and then I can write import OS, and we can say that os dot environment, and then we can give it tf underscore cpp underscore minimum underscore log underscore level. So we want the minimum level of logging, so that's why we are writing this. And this is not round brackets, these are square brackets, and then we are going to write equals to 3. So if we run this again, and this time it should not give us all those warnings. So there you go. As you can see, now we have no warnings at all. So that is good. So now we are moving on to step number 9, and step number 9 is the main step where we are basically training our model. So to train, actually it's fairly simple. We are going to write that model dot fit, and then we are going to input the images and the steering. But again, we are not directly inputting them, we are creating batches of them and then sending it to our model to fit. So we will write here batch generator, and inside that we are going to send our training data, which will be xtrain, and then we also have ytrain. And as you know, we have to give the batch size, so let's say 10, and then we have to say whether it's training or not. So we are going to say that it is true, it is the training batch. Next we are going to write the steps per epoch, and that we will put, let's say, as 20. Now I'm putting very low values so that we can see the complete process running. Once we have seen it, then we will put actual values to run it. Then we will write the epochs, let's say 2 epochs, and then we are going to send in the validation data. So again, we need the generator, So we will write validation data is equals to batch generator, and then we have the validation and then the y validation, and then we have the batch size. So let's put again 20, and then we are going to say that this is not the training data, and then we will say that validation steps, let's say, how much did we put before? We put 20 for the training, so let's put 20 again for this as well, and let's put this as 10. And after that, okay, let's run this first. So let's run this. And there we go. So now you can see that our training was completed. We trained 20 batches, and each batch had 10 images inside of it. So this is the steps per epoch. So these are 20, and we have a total number of 2 epochs. So that's why we have 2 epochs here, 1 by 2 and then 2 by 2. And this is basically the validation steps. So this is the validation loss after it has done the validation steps. So as you can see, our training loss is 0.13 and our validation loss is 0.05. And what we can do is we can keep on training, and it will hopefully get lower and lower. Before we actually put the correct parameters and run it, what we will do is we will move on to step number 10, which is basically saving and plotting our model. So once we have seen that we are able to save and plot the data properly, then we will put the actual parameters so it can take its time to actually train the model. So at step number 10, we are going to write model.save, and we simply have to give it a name. So we can say model.h5. So h5 is the file extension, and basically what this does is it saves the weights, and it saves also the architecture of your model. So then we can simply print that our model is saved. Then we can plot our validation and training loss. So to do that, we can save here the history. History is equals to this, and we can go down and we can write here plt.plot, and we can write here history, and then inside that we want to plot the loss. And we also want to let's duplicate this, and we also want to plot the validation loss. So validation underscore loss, and then we are going to add a legend and some title. So we will write here plt.legend, and we are going to give in training, and then we have validation. Then we will write plt.title, and the title we can say that these are the losses, and then we can write plt.xlabel as the epoch, and at the end we can write plt.show. So hopefully there are no mistakes. So let's run this. So there we go. So now we have the training and the validation loss, as you can see, and then you can see we have also saved the model at the end. Now you can see that this graph looks a little bit weird because the y-axis is not from 0 to 1. If you want to do that, I believe the function here should be plt dot y limit, and you can set the limit from 0 to 1. Let's run that. And there you go. So now our limit is from 0 to 1, and you can, so we are starting from a low loss and we are going down, as you can see. So you can use whichever plot you prefer. So now coming back to our actual values, we can generate 100 images per each step, and we can have, let's say, 300 steps. So this will give us 30,000 images per epoch. So it will train 30,000 images, and we can have it train 10 times. So it will train 10 times 30,000 images, and every time it trains, it will generate a batch of, let's say, 100 images as well, and it will validate that, let's say, so for the steps we can put, let's say, 200. So it will validate 200 steps, and each step it will generate 100 images. So if we run this model again, now it will not take just 1 second, it will take quite a bit of time. Now if you are running on CPU, it will take much longer, but again the idea is the same and it should work as well. But if you are running on GPU, it will be much faster. So now you can see that the training has started, and you can see that the estimated time is about 1.5 minutes for each epoch, and we have a total of 10 epochs, and we are generating 300 batches, and each batch will contain 100 images. So one thing I did not show earlier was the model.h. So once it is saved, it will basically save it to model.h5, and we can use this file to actually test our model that we will do next. So I will stop the recording here because this will take a while, and then once it's done, we will come back and we will look at how it worked. So this is it for today's video. In the final part, we are going to train our model and we will test it back on the self-driving simulator. If you like the video, give it a thumbs up, and I will see you in the next one.